Hi, everyone. Let's begin. Can you hear me? Does this mic work?
Yes.
Okay, thank you. Yeah, sorry for the late start. I had some technical troubles. Yeah, if you have your laptop, could you please just like fold it and put it away? Thank you. Yeah. So before we start the actual lecture, I have a couple of announcements. A bunch of people asked me about increasing the class capacity after the last lecture, so it was 50, now it's 100. Thanks for those who have filled out the survey. If you haven't filled it out, it's due tomorrow by 5 p.m. But based on the preliminary results, one of the questions is, would you prefer the office hours in person or online? And based on the results of the survey, it's pretty mixed. So we're deciding to do like half and half. Abhishek will have his office hours in person on Mondays in this room in class, which is the CSE TA room. And this is the instructions to get in, and I will post that on Canvas as well. And just a couple of reminders, the survey is due tomorrow at 5. Homework 1 is out. It is due in about a week and a half. And the pre-proposal is due next Thursday. Any questions, concerns? Thank you. Okay. This is just something to answer one of the questions. So after class, last lecture, somebody asked about superlinear speedup. In the lecture, I mentioned Gustafson, not Gustafson. I mentioned Amdahl's law, which says that your speedup is bounded by p if you have p processors, and is bounded at most by p. And if you have any serial fraction in your code, the speedup is less than p, and the speedup is bounded. The speedup that you can possibly achieve is less and less as you get more of a serial fraction. So in theory, the maximum that you could possibly get is p. In practice, there are some cases that you might achieve more than p speedup. And I looked into this and I found this interesting paper called Superlinear Speedup in HPC System, Why and When. So this is from 2016. And they go into some details about some different cases that you can achieve more than p speedup, even though like theoretically you can't. One main reason is because of cache effects. So the reason is that when you go to more than one core, you get more cache memory allowed to your program. So this is the illustration from the paper. In the figure, this is what you get when you run on one core. You have C1, you have C0, and C0 has a private L1 and L2 cache, and you have a shared L3 cache in the L4 and further down. So if your problem doesn't fit in L1 and L2, then you're kind of out of luck, you have to go to L3. However, when you have multiple cores, like for example, let's say you run on all 4 of these, you get each one of them has L1 and L2. And the problem still may not fit in each individual one, but the subproblems may fit in them, possibly, depending on how you coded it up. And more importantly, the L3 is shared. So if one core loads some data into L3, and like let's say C0 loads some data into L3 because it needed it, and C1 later needs that same data, it looks into L3 and it doesn't need to bring it in further from DRAM, it can just get it from cache, so it can speed up the other cores as well. So that's one way that you can get superlinear speedup. It's basically through caching effects. Yes.
What's the reason for including L3 in CPU and taking out L4, like going to the picture?
Oh, I see. Like, why is this further down?
Yeah.
Just this will be the subject of today's lecture. Is why do we have multiple levels?
Screen is not changed on the Zoom.
The screen hasn't changed on the Zoom. Oh, maybe? Yes. Did that work? Is that better? Thank you. Cool. So yes, and today's lecture will be about caching. Yeah, so like I said, the topic of today's class is memory hierarchy and matrix multiplication. This is a class about HPC, but we're going to start with single processors, which might at first be a little bit disappointing because we're going to talk about larger distributed computing. So why do we're even going to go to multiple threads? So why should we care about one processor? So like I said in yesterday's lecture, there's this processor memory gap. This is the figure for yesterday's lecture. Again, this is the normalized performance improvement over time, and this is the trend over time. And this top line is processor speeds. So this is how many flops you can do per second or over any time scale. And this is your memory speed. And you can see that the memory speed is lagging way behind the processor speed. And this is like a gap of over 2,000 times. So even if you can do your clock really fast, it doesn't matter if you don't have the data to operate on. So in fact, a lot of applications are what we call memory bound, which means that they are bottlenecked by memory speeds. And often they can run at less than 10% of peak performance, where peak performance is defined by the number of flops you can do per second because of memory limitations. And so a lot of your performance, whether in single node or multi-node, is dependent on data movement. It matters actually even more in multi-node because, in my opinion, communication is basically data movement. So we still continue to care about locality. Another reason that we would care about serial performance in a course on high performance computing. So this is one example. This is dense matrix multiply. And this is an example of the kind of performance optimizations you can do and what kind of speed you can get. So this is the size of your matrix, and this is the runtime. Sorry, I flipped these better arrays down. But anyway, so this green line is the most naive method you can possibly do. You just write 3 loops to do your matrix multiply, and you can see it has the worst performance, it's the highest one. This red one is 1 thread optimized, and you can see that it here is over 100 times better, even with single core optimizations. And doing 8 threads will get you at most 8x improvement, largely low memory effects. And this is what you do when you go to different platforms. So you can see that there's a huge gap here, even if you do single node optimization, even if you do single threaded optimizations. And this is true for general applications. Starting with a good serial implementation is an important first step to doing a good parallel implementation. In other words, if you start with a slow serial implementation, you're going to get a slow parallel implementation over the best possible thing you could get. So ideally, you optimize 1 thread first, and then you do parallelization. And another reason for that is just sort of also ease of programming. It is easier to debug it when you have 1 thread rather than multiple threads, because you can more easily isolate your issues. And matrix multiply is an extreme case, but you can often get at least 10x or possibly even more, depending on what kind of sequential optimizations and what kind of application you have.
Well, the reason for having good performance for the most optimized versions for large matrices, but like for the small ones, it's the one's the worst. Why does it happen?
Oh, you mean?
No, I mean the
Oh, this
yeah,
one?
this one.
Probably because of data movement. So like to start up on the GPU, you have to move. It actually costs a lot to move data from your host into the GPU. And probably for the small sizes, that dominates the cost of actually doing the computation. That's my guess. Good question. Oh, sorry. For the folks online, the question was why at the beginning is the 3 loop not the worst one? Yes.
The emojis are lowest, right?
Yes, sorry, they're reversed. Down is good. I bet. I'll fix that and upload it. Thank you. Okay. So to try to optimize on 1 thread, first we need to define a cost model and a way to analyze our algorithms. So this is an idealized version of what our single processor would look like. We have this processor, and the processor has control flow and arithmetic. And there's some connected memory, which holds all the data, and you can load variables and store into the memory. This is what you basically get in any introduction, any algorithms class that's not like a parallel computing or a high performance class. Your processor can name your variables, so like traditional types like ints and floats. You can do operations like addition, arithmetic, logical operations like shift or and or and things like that. And you can do control flow. You can do branch statements like if statements and loops like for, while, stuff like that. And so when we try to, usually in Big O, when we measure cost, we measure the cost in terms of arithmetic operations. And we kind of assume that writing the variables is free in an asymptotic sense. Like once we're usually not reading and writing that much more than arithmetic. So in a Big O sense, it kind of just goes away. In reality, processors have registers, which are these small in-processor tiny amounts of memory, and the variables have to be loaded from the memory into the registers before you can do any computation on them. And you can load and store the variables between the registers and the memory. And actually, also in reality, unfortunately, control flow is not free. And the compiler translates higher level languages into lower level instructions that are processed by the registers. So many languages today are compiled. Compilers for languages like C and C++, they check that the program is legal, they translate the program into assembly code, and then they optimize the generated code. So this is what you might write in C, like you want to add A plus B into C, and it translates into the registers, into lower level operations like load, addition onto the registers, and then stored. To manage the registers, these days the compiler does register allocation, which decides which registers to load which variables into. So this is slightly more complicated. Before we had A equals C plus B. Now suppose we want to do a couple more arithmetic operations. You have E equals A plus B and F equals E minus 1. And the compiler loads this into assembly, but it also figures out like where's the overlap between the variables and tries to minimize the number of separate registers you have to use. And they do this through graph coloring nowadays. So they generate this graph of the variables and they choose which variables to load into which registers. And the nodes in the graph are lab ranges, like when are the variables overlapping in time, and the edges connect the lab ranges that are simultaneously live. It first appeared in the 50s, but recently since the 80s, I guess not that recently, since the 80s, they've been doing it with graph coloring. Like I mentioned, in addition to doing this translation, compilers also do optimization. And there's this huge space of optimizations that compilers can do. They can do loop unrolling, which is when you have a loop, like you would write like, oh, never mind. You write like for I 0 to n, for example, like C of I plus A of I plus B of I. So this is the regular for loop that you might write, but loop unrolling tries to amortize the cost of this control overhead. This is control. So instead you do like for I up to n, but you do plus equals 4, and then you do this thing, but multiplied by 4. So like I plus 1, I plus 2, I plus 3. And that would be a loop unrolling by 4, but you can do even more. That is usually done automatically by the compiler. It can do loop interchange, which is it rearranges the loops. It can reorder them if it maintains the correctness. It can eliminate dead code. So if it can at compile time determine that the branch is never taken, it can just remove that part from the compilation. It can do reordering of instructions. So if you can legally reorder the instructions, you can improve the register reuse. You can reduce the expense of operations. So like, for example, you would prefer to shift left rather than multiply because it turns out that shifting is cheaper than doing multiplication in terms of arithmetic operations. Loop vectorization, you can sometimes automatically do that, which means that you use SIMD, like single instruction multiple data. And so this sounds like really good. The compiler can do a lot already for you. So why are we still here? Because the compiler may not do everything that you want it to, or as much as you want it to. Yes.
Where did you use number 4? I mean, I can't read where 4 comes from.
This 4?
Yeah.
4 is just like an example. Loop unrolling is like, rather than coming back to this control. So like when you translate this to assembly, you would have, this is some control flow, and then you have like a jump at the bottom, and then you have this as like the assembly that I showed earlier. But instead, rather than having to do the jump every single addition, you do the jump only like every 4 additions.
Oh, so you copy it and then you do the jump at the bottom. So you do
Yeah, exactly. Yeah, you do
and then
you as the programmer write this, but the compiler under the hood writes this into assembly. Is this loop vectorization? If it uses SIMD, then it would be loop vectorization. But like as this is, it doesn't like, so this, so in the, let me go back a little bit. So in this example, you would have like R3 equals R1 plus R2. This is still scalar. If you had like, the vector dictionary instructions are like VAdd, and then you would have like, instead of R3, you have like special vector registers that are like different, differently named, and then you would have to load these 4 things into the vector register. And that might also happen due to the compiler, but not always. Yes,
You might using another color itself.
yes, sorry. The one that I first tried was dead, and then I gave it up. Okay, yes. This is actually. So let me just review that. So this is like the original thing that you might have, where I equals 0 up to n, like C of I equals A of I plus B of I. And then unrolling would be like for still I 0 to n, but then you have plus equals 4 instead of plus equals 1. And then you would have this, but like C I plus 1, I plus 2. That makes sense? Mhm. Yep, thank you. Any questions? The question, sorry, I think I forgot to repeat for the folks online. The question was, what does it mean to unroll because control isn't free? So when you translate this into assembly, this looks something like you have some kind of I variable loaded into a register, for example, R1. And then every time around, you would have to do like I plus 1. And then you have to do like C equals A plus B, loaded this into registers, and then you have to like jump back here. And then you have to increment I again, and so on. I guess I plus 1 is probably down here, actually. But like this, and this is not free. So like this is the actual work that you're trying to do. And this jump actually costs you at least 1 cycle, but possibly more. And this incrementation also costs you. Yeah. Mostly the control flow is more expensive than this one addition. You'll have to do it anyway here. But yes.
What is the difference between the interchange loops and the reordering instructions?
The question was, what is the difference between loop interchange and reordering instructions? Interchanging loop would be like, if you have like for I something and then for J something. If it was better for some reason to do like for J instead, and then for I. Like swapping the order, if it was correct and better for some reason, the compiler might be able to do this for you. Yep. Yes. And there's a whole lecture on OpenCourseware about what compilers can and cannot do that goes more into detail about compiler optimizations. So actually, I think somebody the other day asked me like, why can compilers not save us and why are we still doing this? It's a good question. So I do a little research. There's something called Prosting's law, which is not kind of like Moore's law, I guess, but again, like these are not like physical laws, they're not like Newton's law, but it says that compilers double their performance every 18 years. And when I tried to look this up, the person who said it, maybe they were being facetious because I couldn't find actual data from them to support this claim. But there is somebody later that wrote a paper in 2001 to try to support this claim. So they run this compiler on Spec 95, which is a benchmark suite that has both integer and floating point applications. And this is the floating point results. These are the benchmarks that they ran. And basically they run it with no compiler optimizations, which is the base performance. And then they run it with the highest level of optimization that you can do with the compiler, which is peak performance. And they measure the ratio of improvement. And this is kind of like all the optimizations that the compiler can do from like the dawn of compiler research to today, or to 2001, I guess. And they found that on average, the average ratio between the optimized and unoptimized is 8.1. So if you say that compiler research has been going from 1955 which is 40 years, 45 years from 2001. So you have about 8x over 45 years, which is doubling every about 50 years or so. And yeah, but compilers are good, maybe for other applications or like specific applications. This is not to say that compiler research is useless. Like I think nowadays you can do a lot of domain-specific compilation, and that might help you. They also did this study, like this is table 2. On table 1, they did it for integer applications, and the results were even worse. I think they got like 3x rather than the 8x on average. So they found that compilers are better at optimizing scientific applications that do floating point, but not that well, because it is about 8x. Compared to Moore's law, which gives you 2x every 2 years. What are the numbers? I think
Seems like higher is better.
yeah, higher is better. Maybe it's flops. Like flops per second,
Oh,
possibly. Good point, because they don't actually say it here. So maybe this is a lesson in people that you should say your units. But I would guess flops. I can check it again and let you know next class. Yes.
Unlike Moore's law, where Moore's law says, processors flops doubles every 2 years or something. It's a hardware property, right? But this is a software property.
Yes.
It's our ability to double.
Sorry.
It's our ability to double, optimize things every 3 years. Like, how can we say that?
You think that, or sorry, are you trying to say that like, in theory, compilers could double it every 3 years? Is that what you mean?
No, Moore's law is more hardware, like it's more physical system.
Mhm.
This is like our capability to come up with optimized solutions.
Yes. This is like the ability of compilers to optimize
Yeah,
general applications.
okay, but then it's not intrinsic, like Moore's law is intrinsic, it depends on the hardware.
I mean, Moore's law is a result of hardware improvements. Like people worked on hardware to get Moore's law. Does that make sense? Yeah, like people work on compilers to get this also. Thanks. So as promised, we're going to talk about memory hierarchies. So memory accesses, load and stores have 2 main costs. The first one is latency, which is the cost to load or store one word. Second one is bandwidth, which is the average rate to load or store a large chunk of data. The bandwidth, when we think about bandwidth, is that like this type, low bandwidth is like you have a small rate of flow, and higher bandwidth is like you have more stuff moving per unit time. Latency is delay due to data travel time. Latency is fixed no matter like how big of a thing you're moving. So low latency would be like you have this shorter path, but higher latency would be like if you have a longer thing to move through. So again, there's this kind of sad story with memory, which is that it grows much slower than the rate of flops. Memory bandwidth is very slow compared to Moore's law. So this ratio. This is also, no, this is not flipped. Down is good. Yeah, down is good. This is time, and this is telling us that memory bandwidth is increasing 2x every 5 or so years. On the other hand, memory latency is way worse than memory bandwidth. Oh yes, this is flops per memory access. Sorry, okay. So down is good, because you want, if the machine was balanced, the flops, this would be 1, like flops would be equal to cost of memory access. This is how many flops that it takes you to do 1 memory access. And the top one is memory latency. And here you can see that the cost of memory latency is way higher than the cost of memory bandwidth in terms of flops. So to get around these issues, people take advantage of locality in their programs. There are 2 main kinds of locality. The first one is spatial locality, which is how many accesses an algorithm can make to nearby data over a short period of time. And that is optimizing for bandwidth. So like stuff like cache lines, you take advantage of multiple elements transferred together. Second one is temporal locality, how many repeated accesses an algorithm makes to the same data over a short period of time. So if you have some data and you come back to it, this makes it efficient use of your cache, which is your memory hierarchy. Sorry, for the folks with the laptop, could you close it? Thank you. So the memory hierarchy, this is like a cartoon of a memory hierarchy and what it looks like. This is similar to what we saw in the beginning, where you have these different levels, L1, L2, L3, and you have DRAM even further down. The memory hierarchy takes advantage of locality to speed up the average case. So in the worst case, like if you are accessing completely random memory, this is not going to help you because more recent stuff gets brought into these caches. And if you're accessing something far away, then you're just going to have to get it no matter what. But it turns out that in practice, a lot of your programs can be optimized to use nearby data, or can be used to use nearby data both either in space or time or both. A cache is this fast, expensive memory that keeps a copy of the data. So you have all your data either in DRAM or disk, and the cache just keeps a copy of it for faster access. And it's hidden from your software. So you don't, as the programmer, you don't have to manually manage the cache at all. It's just managed by the OS. So there's several main features of your cache, but the first one is cache line length, which is how many bytes are loaded together in one entry. Often the cache line is 64 bytes. So when you read an element, it turns out that in the cache hierarchy, you don't just get one element, you get the 64 bytes around that thing. So even though a float is 8 bytes or an int is 4, you actually get the 64 around your float or int. And the cache is managed by addresses. So this is what your the cache and the memory are managed by addresses. So this is what your memory looks like. You have some memory addresses here, where they are, and these are the values of your memory. Here, it's example of 42 and 13 and so on and so on. And if you were to bring these things into cache, your cache stores the elements based on the address, but because it's not big enough to store everything in memory, the addresses are not exactly the same. So like multiple things might get mapped to the same location. And here in this diagram, for ease of illustration, they're all different. But because like this is lower, or the lower bits in this one are 10, but the 10 bits in the lower 10 bits like repeat here. So if you wanted to hold this one in the cache, it would also be in the same location. So you have this memory and you have this cache, which is closer to the processor. And the processor again has these two parts, control arithmetic registers. And when you look for an element from your processor, you can either hit or miss in your cache. Hit means that it was there. So it happens to be here. But when you look for this one, which is not pictured even in this, so it's not in the cache, that's a miss. And a miss means that you have to fetch it from the memory.
So why don't we store the full addresses in the cache?
Why don't you store the full addresses in the cache? Because later on, I'll show you more detailed example, but because you don't need to. Like, if the cache is, for example, storing these lower bits, then these lower bits, you don't need to store them in. Like, if the cache is only these 4 slots, and implicitly you have these 4 bits here, you wouldn't, or these 2 bits as your location, that's implicit, and you only need to store the upper 4.
Okay, I'm just wondering how the processor would realize whether the address that it's trying to look for in the cache, like, because we don't have, if you have only 2 least significant bits, right, and we have address that the processor is looking for, but then we have to anyway to map somehow back to the memory to know whether it's really there or not. But we don't do this obviously because it's just a memory access, so the cache wouldn't make any sense.
Yeah.
So I'm just wondering how the processor realizes that the value in the cache actually corresponds to the address that the processor is looking for.
Yeah, so suppose the processor asks, well, let's say this example, like you have 4 slots in your cache. You know, these are implicit, like 0, 0, 0, 1, 1, 0, 1, 1. And suppose like you have data, and then you have tag, and tag is like the upper bits. And suppose the upper ones were like, I'm just making up, like 1, 1. And so the processor asks for a memory location like 1, 0, 1, 1. from here, you can reconstruct 1100, which is the actual memory location that was here. And so you would miss because this. Sorry. 100, maybe a better example. So even though the lower two bits are the same, like you would have to look in here for this address. And you'd also have, like for this, you would also look in here. But because you can read both of these, you can reconstruct the total address and then you find that you got this, but this was not here.
Okay, so we also store in tags that allow us to reconstruct the full address.
Mhm.
And why do we do so? Why don't we just store the address itself?
Space, probably.
Okay, but isn't it the same amount of space if we're using a tag? Because, or is it like work somehow that we really use less space using a tag? Because in this example, the exact amount of space would you have had the full address in, right?
But this is, you only store the tag, like this is implicit.
Mhm.
So here you'd have
Oh.
store 2 bits,
Okay.
but if you want to store the whole thing, you'd do 4. Yeah, and there's a bunch of different ways to, so this is kind of good, this is just what I was saying, like we have this tag, and you have set, which is the location. Set is the location that it goes to. So this is like, in this example, it was 00, and tag is like the upper bits, which is, you can reconstruct the total address with that. And so one way to implement your cache is called direct map, which is you just use the address to locate exactly where you should go in the cache. So this example is direct map. Every address has one location that I could possibly go into. Because like here, we only had one slot of data. One word. Yep. And based on your total address, you can determine the exact location that you should go in your cache. And then you either, so then you look in there, and if it is there, then you did a hit, otherwise it's a miss, and then you have to evict what was there. Another way that you could implement a cache is fully associative, which means that any element or any address can go to anywhere in the cache. So like, instead of this being ordered like 001, this could just be anything, like could be 00, 10, 11, like anything like that. And so this, in some sense, is the best for space usage, because for direct map cache, like even if there is still space in the cache, if your particular location is full, then you cannot use any of the rest of the space. But for fully associative cache, you can use any space in the cache. But with the downside of if you look for something, you have to look in the entire cache because there's no set location that it might be in. So you kind of trade off like efficient space usage for search time. And ideally, you would like both. And I think I mentioned this a little bit, but when the cache becomes full, you have to evict a block. So this is your cache, which is way smaller than your memory. And if your cache becomes full, you have to kick something out. And the way that you determine when to kick something out is called the replacement policy. In reality, most caches use something in the middle of direct map and fully associative, which is called set associative. So they do use the address to determine where you should go in the cache. But instead of having one location where you could possibly go, you kind of have multiple slots per cat. Multiple slots per second, sorry. So here, like instead of one data, you would actually have like a four-way would be like 4 slots per set. And then that's 4-way set associative. You can have like 2-way, 8-way. Usually it's powers of 2, but that's set associativity. And K is the number, K-way is the number of possible cache locations you could have for your element. And so therefore, to find your block, to find an element in the cache, you only have to search those K blocks from your set. That makes sense? Are there questions?
Yes, so K in this example would be 2, right? At least it says two ways. Like I would have guessed that K is 4 in this example, but I don't get the line where it says K equals 2-way associativity. What would that be?
I think 2 means how many slots you have in one set.
Yeah,
Okay.
yeah, this is a good point. There should be 2 things. Like if I were to redraw this diagram, it would look like that, this is the memory. And then like, you kind of have like two things. So yeah, it's a good point. Because
So then K will determine how many of the blocks we have, right?
K, yes, so if this was two-way, this would be like K equals 2, and they would be indexed 0 and 1. Okay, so if you were to search for example, like you could store, going back to this example, you could store like 1,000 and 1,100 here in 0, 0. Maybe this figure is too small, but I can draw it a little bigger. So this is your two-way hash. And suppose that you want to, this 0, 0 slot, you could store your memory addresses 1, 1, 0, 0. Here's your implicit and 1, 0, 0, 0 here, and this would be K equals 2.
So and coloring on this picture is just to emphasize that the block sizes for like what are the color centers?
The colors are, they have to match, the colors match the lowest bit. So like the lowest bit is 0 for red and 4 for yellow.
Okay.
And this is just saying that
Yeah, okay, now it's
hash would go together. So there's several types of cache misses. There's 3. The first one is cold miss, which is the first time a cache block is accessed. And no matter what kind of cache you have, like direct map or fully associative or set associative, you have to incur the cold miss because it's just not there. The next one is capacity miss, which is even if you had a fully associative cache, you would have previously evicted that copy. So that means the total thing was full and you would evict it no matter what. And the last one is conflict miss, which means that there's too many blocks from the same set in the cache. So if you had a fully associative cache, you would have been able to keep it. But instead, because you're using either direct map or set associative, there was no space left in the set and it gets evicted. So that's a conflict miss. So fully associative cache only has to incur cold miss and capacity miss, but direct map and set associative also have to incur conflict miss. And conflict misses can be an issue if you have limited associativity. So this is an example of a matrix. Suppose it has 4096 rows and columns, which is 2 to the 15 bytes. Yeah, a double, I guess you just want 2 to the 15 bytes. And suppose that you wanted to store the submatrix A, which is 32 by 32. And so if you wanted to store this entire column, you would have the addresses X equals 2 to the 15, and so on, up to X 31 times 2 to the 15, which is these locations here, this is location X. And they would all fall into the same set, because here the set is 7 bits. And yeah, the lower 7 bits are always the same if you add 2 to the 15. Does that make sense? Yeah, so even though you technically have a space, you don't have enough set space for all of this. So the solution is to use temporary matrix, or you can pad the rows. Okay, so this is getting at the question that you asked earlier, which is why do we have like L1, L2, L3, so on. On-chip caches are fast, so they're much better to access, but they're smaller because there's a trade-off between size and search speed. And if you have a larger cache, you have some delays, you have to add more hardware to do checking, and you have to do, and you get associativity, which lets you hold more data in the cache per set, but then you also have to check it, which takes more time. So these are the levels again, L1 through L3, and then main memory and disk, and the time gets slower, but the size gets bigger. So memory latency is this huge issue in your program, and there's a bunch of ways to deal with it. We were just talking about different kinds of locality. So if you reuse the memories that are ready, if you reuse the memory that's already in your cache, that's temporal locality. And if you move bigger chunks, like if you move more contiguous data through your cache lines, that's spatial locality. So that's taking advantage of your bandwidth. And there's another two ways that you can possibly improve or deal with the memory latency, which take advantage of concurrency. So somebody earlier was mentioning vector operations. So one way is to issue multiple reads and writes in one operation. So, or in one single instruction, which is vectorization. And then another way is to do multiple reads and writes in parallel, which is latency hiding. So your machine can also do prefetching, which means that you fetch the data, and before the data has arrived in your cache, or yeah, before the next data has arrived in your cache, you can try to fetch another one. And so you kind of like overlap the different fetches. And so this is an illustration. So without the prefetching, you have to, this is the total time, and you have to load X, which takes this amount of time, and then you have to get it. And then only until after that, then you can work on X, and then you load Y, and then you start load first fetch, and so on. But with prefetching, you can fetch both of them, not exactly at the same time, but in overlapping times. And then you don't have to wait for X to finish loading before you work on it. And then you can just compute on it after that. So that is prefetching. And it is great if it works, because like if you did need both X and Y, then that would be great, because then you could just compute on it even faster. But the problem is it's really hard to know like what you could need in the future. And prefetchers are a little bit simple in the sense that usually they just fetch contiguous data. If you need to fetch something farther, like it cannot do like pointer chasing, for example, if you have to access arbitrary memory.
Can you prefetch on a single core?
Yes. Yep. Yeah. So you can do this experiment actually. You can try to, like on a single core, you make an array and you just read the entire array front to back, or you could like jump around in the array and you can see how, like, but you still read all the slots and then you count the time. And that's prefetching.
So I didn't get the reason why sometimes it can go wrong. So when can't we use prefetching then?
It's not so much when can you use prefetching, because prefetching, the hardware can do it under the hood for you, and you can also give hints in the software. But it can go wrong if you fetch something that you didn't need. Either the hardware gets something. I guess with the software hints, you probably know, but with the hardware, like it automatically does it. And if it fetches something that you didn't need to access in your program, then you kind of wasted some fetch. But usually it's not too bad. There's another question. I think I missed. Okay. So ideally, we would like to run at bandwidth speeds rather than latency, because latency is much slower. And so to do that, we need concurrency to fetch multiple memory elements at the same time. So there's this little laws from queuing theory, which tells us that concurrency is equal to latency times bandwidth. And so let's work through a small example. For example, let's say the latency of getting something from your memory is 10 seconds. And your bandwidth is 2 bytes per second, which is like how much can flow through. And so concurrency would mean that concurrency is latency times bandwidth, so 10 times 20 means that you have to find 20 bytes. You have to get 20 bytes in flight to reach bandwidth speed rather than latency speed. So you have to find 20 independent things to issue at the same time. And ideally, those 20 things are things that you actually wanted to work on. And this explains how concurrency helps to hide latency, because if you have more concurrency, then then you can work on latency a little bit.
So in this case, the definition of concurrency is basically just the number of independent things, so to say, that we can.
Concurrency
operate
is,
independent.
yeah, so like in terms of the units, this is seconds times bytes per second, so concurrency is just in bytes.
Okay, so is it just data?
Yeah.
That is.
Yes, it's like data volume that you're working on.
Okay.
And this is a real world example of somebody that ran the numbers on a 2005 processor. They found that the latency is 60 nanoseconds and the bandwidth is 6.4 gigabytes per second. And so this is prefetching, you can issue multiple requests before you finish the first one. And so 60 nanoseconds, times 6.4 gigabits per second is 384 bytes, which is this number of cache lines. And so that means that to keep your pipeline, you always have to have 6 cache lines in flight, which is the data volume that you can work on. Oh, and you also need to issue the requests before your latency time. So each request has to be launched at least 60 nanoseconds, because that's the latency before your data is needed, to have your data like available when you need it. Okay, cool. That was a lot. Other questions?
In the L1, L2, L3, what are those three? Are they like, are they attached to individual processors or are they shared and stuff like that?
Yeah, L1 and L2 is usually private to the processor, and L3 is usually shared.
So
That creates cache consistency issues.
It does. Yes, yeah.
what's the difference if L1 and L2 are both individual? So what's the main difference between those two?
Sorry, for the folks online, the question was, what is the difference between L1 and L2 size? Mostly, yeah, L1 is smaller. I guess size and speed. So next, we're going to talk about the ideal cache model, which will get us into cache analysis. So I think they cover this a little bit, or maybe a lot, in 6220. But actually, in the survey, I found that a lot of folks haven't taken it. So I think this is actually good. So the reason that we're doing this is that previously we're talking about memory issues and how we want to optimize for memory. And the ideal cache model is a way to do theoretical analysis in a big O sense on memory issues and how memory friendly your program is. So the ideal cache model is this refinement of this classical RAM model that you see in a lot of algorithms classes. So in the RAM model, you just have one processor and you have like a flat memory, and it costs you the same amount to access anything in your flat memory. However, in the ideal cache model, you have this 2-level hierarchy. You have the processor, then the cache. You have your processor, and instead of your flat memory in the RAM model, you have the cache, and you have your memory. And your cache is n over b cache lines, and each cache line is size b. So again, usually b is 64 bytes, but in a theoretical sense, b can be anything, and m is also a theoretical value. But, so I guess one way to think about this model is that there's only one cache and there's only one memory. So like we were talking about how there's L1, L2, L3, and so on, and why doesn't this capture all of that? And the reason is because that it would be more complicated to capture so many levels of cache. And this is like an approximation of one slow memory and fast memory. Yeah, so your cache size is m bytes, the cache line size is b bytes, and you have m over b cache lines. And because this is the ideal cache, we are not thinking about associativity or replacement. And so we just assume that's fully associative and that the replacement policy is optimal and we don't have to deal with it. And in this model, we have 2 performance measures. One is work, which is the normal running time that you would do in Big O. And the second one is cache misses Q, which is the number of cache lines that you needed to transfer between cache and memory to do your algorithm. And so ideally, work upper bounds Q, but you prefer to have Q less than W if you're using the cache efficiently. So we made these assumptions about the cache, about like the replacement policy and the associativity. How reasonable is that? There's this famous theorem from 1985 from Schlieder and Tarjan that says, suppose an algorithm has Q cache misses in ideal cache of size m. If you have this fully associative cache of size 2m that uses this least recently used eviction policy, which is this eviction policy that keeps track of when things came, and when you get full, you just kick out what was least recently used or what you just accessed farthest in the past. Then you incur at most 2 Q cache misses. So this is within a factor. This is a constant factor. So in the asymptotics, it goes away in a big O sense. And this is like a kind of simple theorem when they proved it, but actually I came up with this idea. So the fact that they use 2m here rather than m is called resource augmentation, which is a cool theoretical technique that you kind of like, you give an online algorithm more resources than an offline algorithm. Yeah, and the implication of this is that for asymptotic analysis, you can assume optimal or LRU with only a constant factor difference. And what this means for software engineering is that you can design a theoretically good algorithm in the ideal cache model. You can engineer for detailed performance based on your actual cache parameters and your like stuff like associativity. And because real caches are not fully associative, and if you need to deal with even finer grain, in reality, loads and stores have different costs from each other. Like stores are more expensive with respect to bandwidth and latency.
So this is. So it's saying like, okay, if you have Q caches on a cache size M, if in an ideal cache. Then with 2M on, a normal cache, you get 2 Q cache misses, but that doesn't. How do you know that like, if you had a cache size M, you would still get linear?
You would not.
Oh,
Yeah, you would get a factor of K, or you would get a factor of M at worst.
I mean,
Difference. Like if the perfect replacement policy had the same size as the LRU, they would not have within a constant factor of cache misses.
okay.
But because like in some sense this is like giving more power to the offline algorithm or giving more power to the online algorithm.
Can this be extended to like set associative caches as well?
Can this theorem be used for set associative caches? If you gave the set associative cache enough augmentation, you could simulate a fully associative cache. With less augmentation than that, I'm not sure. Sorry. So like, let me think about it and maybe get back to you with a better answer. So like, in the extreme, like your set is, for example, 2. And if you augmented this so that your set was equal to M, then like, yes, each set would now simulate one of your original caches. But I actually am not sure if you augment less than that. So let me think about it a little bit and I'll tell you later. Thank you.
You mentioned online and offline algorithms. What are those?
Offline algorithm means like an algorithm that has knowledge of the future. An online algorithm means you don't have knowledge of the future and your input is coming one by one. So this perfect replacement policy would know the future of all your memory requests and it could upfront decide what to evict when. But this least recently used is an online algorithm, which means like it doesn't have any knowledge of the future and it just looks at the previous time to make its decision. Sorry. Thank you. Thank you. Okay. Yeah, so we're going to use this model to do a warm-up for analyzing cache misses. So suppose that your program reads the set of data segments. You have R data segments, and each one has S sub 1 bytes. And then suppose that when you sum up all of them, you get N bytes, which is less than your memory size of over 3. And on average, each of your data segments is at least size B. So we're going to bound, and this is useful for when we want to reach submatrices. So like you could think of this as your R data segments are each of the rows in your matrix. And so then all your segments would fit into your cache because this total size is less than n, and the number of misses to read them all into your cache was at most bounded by 3n over b, where b is your cache line size and n is the total number of bytes in your data. And the way to reason about that is this is an illustration of your segment, and the worst case is you get kind of a spillover to the left and the right. So in the worst case, you might have to read about 2 extra cache lines per segment. But you do get cache locality in this intermediate part in your segment. So that's where this overview comes from. But worse, even if you're reading B blocks at a time, you get a constant factor. You get a constant factor 3n over b. Whereas in the very best case scenario, you would have to read n over b. Like if these align perfectly with endpoints. Another assumption that we have to make in the ideal cache model is that the cache is tall, which means that the cache size is at least b squared. So that means that you can hold like a B by B. Basically, the reason that we want this is that we want to be able to hold a B by B submatrix in the cache. And this is pretty true in modern machines. Like this is an example of an Intel Xeon. The cache line size is 64 bytes, and the L1 cache size is 32 kilobytes, which is way bigger than 64 squared. And like I said, the reason that we have to make this assumption is that even if you didn't have B squared, even if your submatrix was technically you had enough bytes in your cache to store it, you wouldn't have enough lines. Does that make sense? Okay. I'm not sure that one. I mean, this is just a straightforward extension of the thing that we were talking about earlier. So again, like I said, the reason that we're doing all of that is to try to prove something about holding submatrices in your cache. And so if you have this n by n submatrix here, and you have this tall cache, and your submatrix can fit in the cache, then you at most have to read basically your size of your submatrix within a constant factor over B. So that is the model. And that is also a lot, but we're going to use it to do matrix multiplication. So why do we care about dense matrix multiplication? It's an important kernel in a lot of problems. Dense linear algebra is a motif in pretty much every list of scientific computing applications. It's related to a lot of other algorithms, like you can use matrix multiply to do transitive closure on graphs, and it dominates the running time in deep learning. And it's a good model problem. They should say well studied. Sorry, just a typo. It's a good model problem. It illustrates a lot of the techniques that we're talking about for locality optimization, and it's easy to find good libraries like Intel MKL. Yeah, and this is what matrix multiply looks like. You have matrices, and you have A times B equals C, and for this entry of C, it corresponds to this row and this column. Okay, so this is the most simple way that you can multiply square matrices. Let's start with square matrices because it's easier to do the code for it. So suppose your matrix is n by n, and we want to multiply it. You can write these three loops, I, j, and k, and we do it C. For every entry of C, you have to go through a row of A and a column of J, and that's a row of, this is a row of A, so like so row I, and then you increment by K, and this is column J, and then you do it. Oh, I guess, yeah, so the way that you store these matrices is what is called row major. So if you have your matrix A, like here, this is A0, A1, and so on. The way that you lay it out in memory, A0, and so on. So you just put the rows like end to end in your memory because your memory looks flat from a programmer's perspective. And so that's why you have to do the indexing like that. And so this is straightforwardly n cubed work. There are 3 loops. Each one has n iterations in it. So that's n times n times n, which is n cubed. Oh, oops, I guess I already just said this, but in this code, they're in row major order. It's exactly what I was saying. You have these rows in the matrix and you just put them end to end.
Did that last code example assume that it was a uniform matrix?
It is, yeah, it assumes that it's square because otherwise the code becomes a bit more complicated and you would need like 3 variables rather than just 1 for the size. Thank you. Okay, so they're laid out in row major order. And we're going to use this ideal cache model to analyze the cache misses. So we have this row major order and we have a tall cache, as we were saying before. And so the first case, suppose that your size n is at least m over b, which is the number of lines that you have in your cache. And so we're going to analyze the cost to average matrix b. assume that we have LRU. This is A, so we're gonna read through it like this. And this is B, so we're gonna read through it like this. And the number of cache misses is theta of n cubed, because we incur a cache miss on every axis. Because the length of your size is at least m over v, and so when we jump down one row in the column, that's greater than m over v, which is greater than the cache size, so it's not in the cache. Yeah. The next case is if your site length size n is at least square root of m, but still less than your cache size. And so again, we have the same matrix axis pattern, but now the case was slightly better. You have n axes in your row, and yeah, and each one, sorry, you have n squared over b to access your matrix B, because you can take advantage of spatial locality, because now n is less than your memory size. Then finally, this is kind of like the best case in some sense. If your matrix size is less than square root, or if your length size is less than square root, and the n squared, which is the size of the matrix, is less than m. So then the entire thing fits in the cache, and you don't have to keep reading it again and again. Okay, yeah, so earlier we were talking about loop interchange. Originally, I had written this ijk. If you swap the loop to become ikj, we can analyze what happens if you do that. You can convince yourself that this is still correct. You're just swapping the order of the loops, it doesn't change the inner kernel. Again, I'm going to access this major B, I'm going to access this matrix B, but instead of accessing it column-wise like this, now we're going to access it this way. And now we can always get spatial locality in B, because we're accessing it according to the layout. So now it becomes n cubed over B, whereas in the very worst case before, this was n cubed, because now matrix B can always get spatial locality. Does that make sense? Yeah, I think I can have time to do this. Okay, so this is the last thing that I'm going to talk about today, which is tiling for matrices. It's also called blocking. Tiling is this technique for getting additional locality in your matrix multiply. And basically the way it works is that rather than doing one whole row and one whole column at a time, it cuts up the matrix into these blocks, these S by S blocks, and it does these local matrix multiplies on each block. And the way that you implement that is basically by previously we had 3 loops. Now this becomes 6 loops, because each one, rather than doing the whole row, is now just going over like part of the row, and then you have to do the control flow to go into the next part of your block. Yeah, so the code looks a bit more complicated, and this doesn't actually help in terms of the actual number of blocks that you have to do. The work is the same. There are, yeah, so if S is your block size, this is n over s cubed, and then you have s cubed, and the total work is still n. Total number of multiplies and additions you have to do is still empty. Yes. And the reason that we are interested in doing tiling is because it helps in the cache analysis, and therefore, and ideally also in the cache behavior in practice. So using the side cache model again, we're going to analyze the parameters. So first, we're going to make this nice assumption that we know this parameter S that allows us to fit the submatrices into cache. For now, we're not going to deal with how we would find S, but suppose that S with theta of m root m. So then S squared is equal to like theta of m. And so using that submatrix lemma that we were proving earlier, that allows us to do S squared over B. This is per submatrix because each one can fit into the cache. And then so this is the cost to read the submatrix S squared over B. This is the number of tiles that you have to do, n over s cubed. And that gets us theta n cubed B root m in the denominator. This is a bit subtle. So maybe I can say it again. If you knew that your tile could fit into the memory size, you could do. Basically, you could multiply a tile of A and B and get one tile of C, all in cache. Does that make sense? Like previously, we we're going through the rows and the columns, and then you had to do, like by the time you got around to the next row, you already kicked out the first part of your row. This allows you to do an entire tile up front. Like once you brought it into cache, you just do all the computations that you need for the tile, and then you never have to do it again. For that particular submatrix of C. That's kind of like the high level intuition. And so that is why you get, previously the best thing we're seeing was like B in the denominator. But now we have this factor of memory size in the denominator also. And that is because you're using not just spatial locality, but temporal locality as well. For spatial locality, you can only get factors of B. If you have temporal locality, you can sometimes also get factors of M.
I'm a bit confused. So like you can like have that like tile of A and that tile of B, but that is not enough to like get that tile of C, right? You would need like all the
Yeah.
the tiles in that row, right?
Yeah, so like, for example, like just for this tile of C, you would need like all of these tiles of A and all of these tiles of C. Yeah, but like once the first step is like you would multiply this tile of A and this tile of C.
Okay.
But like originally, even for this one entry of A, you had to do like all of this and all of this. Mhm. Yeah. Good question. Thanks. Yes. Yes, of course. So previously, like when we were just doing the 3 loops, we had to go do this whole row of A and this whole column of B to do like this one single entry of C. But then we would need this row of A again to do just like, for example, the second entry in C. And we weren't using temporal locality before because by the time we got back around, we would have kicked out this entry if your matrix was sufficiently big. But now because of the tile, you're just storing, with tiling, you can solve sub-problems rather than the entire problem at once. Does that answer your question? Yes.
So then, when you're tuning S, you need S to allow you to fit like all the relevant rows and columns from A and B, so that you could get that one, like whatever tile of C that you're.
Exactly, yeah, so you would have to pick S such that you can fit one submatrix of A, B, and C to the entire subproblem in cache.
Mm.
So I'm not gonna talk now about how you would pick S, because it's okay.
So like when you have like multiple cores, you would have, and each would have like their own private L1 and L2 cache.
Mhm.
So you would have like multiple cores doing this like tiling separate sections of the matrix to improve the matrix multiplication speed.
When you have multiple cores, you would do, for this one, you would put like a parallel 4 on some of these outer loops. And then each of the cores would be working on different submatrices. So the tile size, if there was just, for example, one parallel 4 up there, each core would have the same submatrix size because they would have the same S. They would just be working on different submatrices in C. Does that answer your question?
But I think we need to add all of those submatrix results into a final result. Because, for example, we have 4 times 4 tiles. It will create 4 submatrix in a loop, right?
Would you have to do synchronization?
But just suppose we are calculating the first tile of the same matrix.
Yeah,
So-
they would be separate, like if, for example, if core 1 was doing this tile of C and core 2 was doing this tile of C, then they would be using the same matrix, they would be using the same parts of A, some of the same parts of A. Because like they are both in the same row, they would be using different parts in B, because they would be like, core 1 would be here and core 2 would be here, so they would be using different columns in B, but they would share A. But they would be writing to different parts of C. And they're just reading from A, so you don't have to do synchronization. Question? Yes. And it turns out that this is optimal for matrix multiply. There's a paper from 81 showing it. Yes, which is great. So like I said, we're not going to talk about how we find S, but it's a good question. Like, given that if you didn't know M up front, it would be really hard to choose it and you'd have to do some tuning. And like I said before, there's not just like the memory model just gives us 2 levels of cache, but in reality, we have L1, L2, L3, and so on. So you actually have many levels. And ideally, to do your actual implementation, if you had L1, if you just have like L1, L2 and main memory, then you would need two parameters, S and T, to fit into L1 and L2. And the issue is that it is real, you can't do binary search to do tuning in 2 dimensions. Like if you had just one tuning parameter S and T, you could do like some kind of like exponential jumping or something in S. But if you have S and T, it's really hard because like if you have increased S, maybe you should have like decreased T. And so like they both depend on each other and it's very hard to tune 2 things at once. And actually you have more than 2 things, you have several levels of cache, so that is even more
But I think
complicated.
they are determined by the size of them.
Yes,
So why do we need to tune those parameters?
like if you wanted to run your code on a different processor, the cache size may change, for example. Yes. So that is one complication with using this type of algorithm, is that it is not super portable if your cache size changes across machines. And yeah, this is what the code would look like for 2-level caching, and then it becomes even more and more complicated. So you probably not want to implement like this. And it becomes even more complicated, actually, like L1, L2, L3, you have 3 levels, and the number of for loops is still growing. And even more complicated, like somebody was mentioning earlier, when you have multiple cores in the shared caches like L3, you have a bunch of cores working, and so you know the total size of L3, but it is not necessarily true that that total size is equally divided up among the cores at any given point in time. And so the effective cache size that you're working with can vary over time, which is even more complicated for picking S and T because like they're not even if you chose them for like the equal size, they're not necessarily correct over the total course of the execution. And so then it's very hard to choose the parameters when you go into the parallel case. Oh, sorry, I'm over the time. So next class, we'll talk about divide and conquer. Thank you.